So our topic for this video is heat transfer in a circular pipe with laminar flow. So Sumit Kumar and I Rajneesh Patel are presenting this video. In this video, assumptions are that the flow is fully developed and there is constant surface heat flux. So in this we have taken a part of the laminar flow, so which is the distance r, this edge, and we have taken this part here. So it is at distance r and this distance this dr. So total will be r plus dr, and this thickness is dx, which is dx. So here qr heat is coming, and here the heat is qr plus dr, which is the radial conduction, and here the axial advection is t, is a t plus del t by del x into dx. So del t by del x is the gradient of temperature in this direction. We have multiplied dx into the slope, means gradient. So in this section, as there is no heat generated, only there is the radial conduction and only the axial advection. So both will be same by the energy balance, and we can write this by q is equal to mcp delta t by this, and in the radial conduction will be this. Axial advection is given by this equation, which is dm dot cp t plus delta t by del x into dx minus t. So we can write qr plus dr in the same way as we have written the change in temperature, which is qr plus del q by del r into dr, which is the this gradient of q into multiplied by dr, as the distance between this thickness is dr. So if we put the third equation is 2 in 2, we will get this equation, which is del qr by dr minus del qr by dr del r into dr equals to dm dot cp del t by del x into dx. So as we know that the radial conduction is also given by qr equals to minus k del t by del x 2 pi r dx, where 2 pi r dx is the curved surface area of the cylinder, which is this small cylinder. So it will be equation number 5. One more time, this both will be equal, because in this section no other source of energy is there, no heat is generated, so both radial conduction and axial advection will be same. After this we have dm dot equals to rho u 2 pi r dr, which we give as the sixth equation, and after this we put fifth, which is this equation, and sixth that equation into this equation. Fourth equation we put 5 and 6 in 4. So after putting this we get this equation del by del r into r del t by del r equals to rho u cp r k by del t by del x, and we put k by rho cp as alpha. So our seventh equation become this. Then we know that there is constant surface heat flux as we have assumed. So heat flux is defined as q double dash equal to h ts minus tm, as ts is the surface temperature and tm is the mean temperature. So after differentiating this will be 0, as q double dash is constant. So dts by dx will be equal to dtm by dx, which is our equation 8. And after this as we know that the flow is fully thermally developed, also we are assuming that the flow is fully thermally developed. So in this case theta, which is non-dimensional gradient, this has to be 0 for fully thermally developed flow, where theta is tsx minus trx by tsx minus tmx, and after solving this we get this. So in this dtx by dx minus dtm by dx should be 0 due to this equation, 8th equation. And then after this dts by dx will be equal to del t by del x, and after and since dts by dx equal to dtm by dx, so we get this equation. Also we have taken the partial derivative of dt because it is dependent on both r and x, and other than t, ts and tm are all dependent on only x. So we have taken the partial derivative of dt and complete derivative of ts and tm. So we will put this ninth equation, which is dtm by dx equals to del t by del x, into equation 7, which is this. And after this we will get this equation. After replacing we will get this equation. We have replaced del t by del x by dtm by dx, and then we know that for laminar flow the ur by um equals to 2 into 1 minus r naught by r naught whole square, where um is the mean velocity. So rearranging we get this, and after we put value of u into equation, we get this equation. And we will assume that the beta will be 2 um by alpha into dtm by dx for further simplification in the calculations.
On solving all the equations, we will get this equation that is del by del r into r del t by del r equal to 2 r upon alpha into 1 minus r by r naught whole square upon into dtm by dx. Let the beta is equal to 2 upon alpha dtm by dx. On integrating this equation, we will get del r del t by del r equal to integral of beta r into 1 minus r upon r whole square into dr. So after simplifying this, we will get r into del t by del r equal to integral of beta r minus beta r cube upon r whole square into dr. So we will finally get this equation r del t by del r equal to beta r square upon 2 minus beta r power 4 upon 4 r naught square plus c1. So on dividing this equation by r, we will get del t by del r is equal to beta r by 2 minus beta r by 4 r naught square plus c1 by r. On integrating this equation, we will get this equal to t r comma x equal to beta r square by 4 minus beta r k power 4 minus 16 r naught square plus c1 ln r plus c2. So again simplifying, we will get t is equal to 2 upon alpha dtm by dx whole bracket r square by 4 minus r k power 4 upon 16 r naught square plus c1 ln r plus c2 related to equation number 11. So on applying boundary condition, let the first boundary condition, that is at r is equal to 0 t r comma x is finite, but on solving this equation number 11, we are getting the value is equal to minus infinity. So we need to make c1 is equal to 0. At r is equal to r naught, t is equal to ts, then ts is equal to beta r naught square upon 4 minus r naught square upon 16 plus c2. From this we will get the value of c2 at ts minus 3 by 16 beta r naught square. Then putting the value of c2 here and c1 is equal to 0 in the previous equation, so we will get t r comma x is equal to um upon alpha dtm dx into r square by 4 minus r k power 4 upon 16 r naught square plus ts minus 3 by 16 into 2 um dtm by dx upon alpha. This is the value of beta into r naught square. So the main equation will be this one. So as we know that the mean temperature for circular tube is Tm is equal to 2 r naught square integral 0 to r naught u dr dr. So putting u is equal to 2 into 1 minus r by r naught whole square, so we will get this equation. So on integrating the equation, we will get Tm is equal to ts minus 11 by 96 beta r naught square, and then putting the value of beta here, so we will get Tm is equal to ts minus 11 by 48 upon alpha r naught square dtm upon dx. Let it be the equation number 12. Since there is a constant surface heat flux, so q double dash is independent of x. So dq convection is equal to q double dash p dx, where p is perimeter, dx is the differential length. And again dq convection is equal to m dot cp dtm, which comes from here, where q convection is equal to m dot cp tm out minus tm in. So dq convection is equal to m dot cp tm plus dtm minus tm. So dq convection is equal to m dot cp dtm. This is like this. On equating this equation, q double dash p dx equal to m dot cp dtm, we will get dtm upon dx is equal to q double dash p upon mcp, and again p is equal to 2 pi r, that is perimeter, so replacing it by pi d. Then putting this equation in previous equation number 12, where then we will get t is equal to ts minus 11 by 48 r naught square by alpha q is double dash pi d upon m dot cp. So again solving, we will get Ts minus 11 by 14 Q double dash S d upon K. By the Newton's law of cooling, as we know that Q double dash is equal to H Ts minus Tm. So replacing here Q is double dash by H Ts minus Tm here. So we will get Hd upon K is equal to 48 by 11, that is 4.36. In this equation, D is diameter, K is where K is thermal conductivity and H is heat transfer coefficient. Hence, for fully developed laminar flow with constant surface heat flux, Nusselt number is constant.
Now I would like to talk something about theta. So theta is the non-dimensional quantity which is defined as tsx minus trx, tsx minus tmx. Its gradient is 0 for the condition of fully thermally developed flow. So previously I was not able to explain this. So theta is this ratio, and for the fully thermally developed flow, its gradient should be 0.